Right, so this video is going to look at catalysis, which kind of comes under the transition metals portion of Unit 5. So we're going to run through what a catalyst is, sort of basically the stuff that you need to know about catalysts, the types of catalyst, and that's probably about it. Then a couple of exam questions at the end. So quite quickly, so then as a start, and should be a sort of a recap really that's kind of GCSE more than anything. What is a catalyst? I'm not going to write anything down here, but a catalyst is something that speeds up a reaction. The key thing is it does so by providing an alternate pathway or an alternate route at a lower activation energy. So it lowers activation energy and therefore speeds up the reaction. So it doesn't provide any more energy. It doesn't give any more energy, the speed particles up, but it speeds up the reaction by lowering the activation energy. So thinking back to sort of Maxwell-Boltzmann curves, we have a higher proportion of molecules or particles that are therefore able to successfully react. It's not used up. That's a very, very important thing that ties into sort of various topics. It's not used up. The catalyst will remain. So, what makes transition metals then good catalysts? Well, they have what's called variable oxidation states. And that means that they can go from, say, M2 plus to M3 plus, and then back again. And they may have multiple different states in. When I talk about states, it's obviously the oxidation states. We're talking about sort of the whole redox thing, which is obviously a key topic within Unit 5 as well. In terms of catalysis, you need to know about two types of catalyst. You need to know about heterogeneous or genius. I don't know really how to say it, but I just say heterogeneous, and homogeneous. Or homogeneous, heterogeneous. It depends how I'm going to say heterogeneous and homogeneous, because it's just how I say it. Hetero, just like heterosexual, where a guy likes a girl, it's the same principle here. You've got differences. That prefix is determining different, Latin or Greek or something. So it's some sort of difference there. We're talking about different phase or state. So we could have gaseous reactants, and our catalyst would be a solid, for example. That would be a heterogeneous catalyst, so it's in relation to the catalyst. Homogeneous, I don't know if I've said that, heterogeneous, I don't know what I'm doing. Homogeneous or homogeneous would be one where it is in the same phase. We can use this term phase, or we can use the term state. So solutions, or aqueous ions, aqueous solutions, whatever, where we're in the same phase, same state. So that's just very quickly a little introduction to catalysts and what I'm going to cover. So I'm going to go through first of all stuff on heterogeneous, then look at homogeneous, and as I said, then do a couple of exam questions. Hopefully this will be reasonably short as a video. So heterogeneous. We're talking about solids invariably that are used normally with gases. And I'm going to go through three particular cases which I think are worthwhile knowing and learning. The first one in particular is really important. Often used in a mesh situation, so we'd have some sort of mesh that basically we would coat the mesh with our catalyst. So we're not throwing in just a massive lump of catalyst, we're attaching it to a mesh. And what that's doing is that's creating a really large surface area, which means as our gases pass through, they're in contact, or there's a lot of gas in contact with a lot of catalyst, which is great because the reaction actually is occurring on the surface of the catalyst. That's actually how a catalyst is working. They have to be in contact with them, otherwise, as far as I'm aware, otherwise they can't actually catalyze a reaction. So the bigger the surface area, the more chance we have really, or the more efficient that catalyst is going to be. So straight on to our first example then, so throw it straight in there. First one is the contact process. This is a process that makes sulfuric acid, and there's one particular stage of it which is often examined, which you are expected to know about, and that's the stage where we turn sulfur dioxide, which is a gas, we react it with oxygen, which is obviously also a gas, to turn that into sulfur trioxide, which is a gas. Now for this we use a solid catalyst, so we use a homogeneous or homogeneous catalyst, and we use vanadium oxide, vanadium 5 oxide, because our Oxidation state here is +5, and obviously -2 like normal, and this is added as a solid. This is the overall reaction that occurs, but it doesn't actually occur, when we break it down, it occurs into 2 steps, or occurs in 2 steps I should say. And the first step involves the catalyst, which is kind of goes slightly against particularly what you learn at GCSE when catalysts not used up, and that's still true. Catalysts are not used up, but they can take part in the reaction, and they just need to be remade. So the first step is our SO2, and I'm going to ignore state symbols because I'm a terrible person, but that's it. Gas, solid, reacts to produce SO3, and what happens is we end up with this different form of vanadium oxide. So my sulfur here is +4, it's been oxidized to +6, and in doing so we've got the vanadium at +5 has been reduced to +4, and this highlights here that, as I said before, the variable oxidation states, in this case vanadium. Now it's not one that's required anymore. Outside of this, vanadium isn't examined anymore, but you've got +5 going down to +4. That was a terribly drawn 4, but that is 4. This though isn't going to act as a catalyst because it's now been used up, or it's been turned into something new. So our second step is the reformation or the reformation of said catalyst. So that reacts with half O2 to produce V2O5, which is great, which is what we want, because we've now made the V2O5 back, and everything's all happy, and everything's sorted. And now we look at this overall reaction-wise, we exclude the V2O4 and the V2O5, and we end up with SO2, or that would cancel when you went through SO2 at half O2 going to SO3 as we've got there, which is great, which is exactly what we want. That is that entire reaction. You need to know these equations, the overall equation and each step. If you don't know it, then you're throwing marks away and you are silly. Haber process is the other one. Haber process is a real common GCSE one. Really simple. It's the reaction where we produce ammonia. So it's an equilibrium one, is often how it's talked about. So we produce ammonia. We do that by reacting it with, I don't know why I've written this backwards. That is bizarre. No idea. Maybe my mind's just gotten broken. So you react nitrogen with hydrogen and you produce ammonia. So obviously in that ratio there. And this one we use an iron catalyst. Again, it's a solid. These are all gases. I'm not going to go through how this works, but actually on the Wikipedia page for the Haber process, because I'm that sad that I look at those things, there is a little rundown of what happens, and actually it's quite, unless it's just been really simplified, it's actually quite straightforward, and it's actually quite interesting how the iron allows the catalysis to take part, and basically how the nitrogen sticks, the bond breaks in between it, the hydrogen sticks, bond breaks, and they end up reforming into this into the ammonia. But it's quite a straightforward thing. It's not required for the exam, but it's quite a nice bit of extra sort of reading to give you a heads up. So I think that's just on the Wikipedia page for the Haber process, but really, really interesting to show particularly how, in this case, these are actually, they're absorbing, they're sticking to the surface, and really highlighting that fact that they must be in contact with the catalyst. As I said before, particularly with this sort of whole mesh situation there, they must be in contact. Okay, the last homogeneous reaction is generally speaking, it's just when we talk about catalytic converters. These are used in cars, and they're used in cars to reduce noxious emissions, bad emissions, particularly ones that would cause acid rain, mostly nitrogen oxide. So we use rhodium. RH is its chemical symbol, rhodium, and again it's on a mesh there, ceramic mesh. And the reaction here, and this is a reaction again that I would learn, we take carbon monoxide and nitrogen monoxide, and we turn that into carbon dioxide. Now, yeah, that's not very good for this sort of whole environment thing in terms of global warming, but this has caused an acid rain, and this is pretty toxic, so it's not great. We don't really want these things to exist. But the catalytic converter, luckily, on the back of your exhaust, or just before the exhaust pipe, or the very end of the exhaust pipe, have a mesh inside there, coated with rhodium, this really precious metal, something I think platinum can use as well. The gases pass through, the reaction occurs on the surface, boom, nice. The only thing to add really to sort of that's it really for homogeneous catalysts. The only thing to add to those is the idea of catalytic poisoning, and this is a really good way to look at this is in catalytic converters. Nowadays we use unleaded petrol rather than, that's me messing around earlier on, trying to get rid of that. We use leaded, no we don't, we use unleaded petrol. Back when I was a a youngster, you had leaded petrol, 5-star and things. Nowadays, you use unleaded petrol, and if you use leaded petrol with the catalytic converter, you actually get what's called catalytic poisoning. And what happens is the lead, essentially, as far as I'm aware, the lead sticks to the surface of the catalyst. And if you imagine you've got your catalyst surface there, and we've now got lead stuck to it, well, these guys can no longer attached and absorbed to the surface, and therefore this reaction can't take place. So that's pretty bad. This is catalytic poisoning. We get stuff that sticks to the surface of the catalyst. The only way around that is either to clean the catalyst and actually to remove, look at that, the wonders of modern technology. We remove that, and now this obviously will work, or we have to replace the catalyst. Both of those are time consuming and they're not very cost effective. So catalytic poisoning is a bad thing, particularly in industry, because it's just going to cost more money, which we clearly don't want. So that's, have I been saying homogeneous this whole time? These are heterogeneous. Sorry, I think I've been saying homogeneous. These are heterogeneous. So if I said homogeneous, I apologise. I think I might have done actually several times. These are heterogeneous because they are in different phases. Make that really, really clear. Gases in the contact process with a solid catalyst. Gases in the Haber process with a solid catalyst. Gases in the catalytic converter situation with a solid catalyst of rhodium. So these are heterogeneous, not homogeneous. I apologise if I said that wrong, which I think I did. This was just me messing around. Get rid of that. Look how blurry those lines were. I wasn't happy. Wasn't happy with the blurry lines. Okay, I'm going to look now at actual homogeneous catalysts. These are, I think, the more difficult side of them. There's more equations to learn. You need to learn these equations, okay? You need to know it. Homogeneous, as I said, same phase. The first one to look at is the reaction between iodide ions and peroxidized sulfate ions, which is S2O8 2-. This reaction, it's a slow reaction. The reason it's slow is because we have repulsion between these two, and therefore it's a slow reaction. It will occur, but it takes a while. So what we can do is we can whack in a catalyst of iron 2+, and this obviously would be added as an aqueous solution. These guys being aqueous as well. We whack that in, and what it does is it reacts with the Fe2+ ions, react with the peroxidized sulfate ions to produce sulfate ions, and in the process the Fe2+ gets oxidized to Fe3+. So we're reducing the peroxidized sulfate ions, and we are oxidizing the iron 2+ ions. Need to balance that up because this is currently not balanced. I believe it's correct. Yeah, so we've got obviously our oxidation states there. I won't bother putting them in because it's quite a straightforward one. Again though, catalyst, it's got to be remade. So our Fe3+, sorry, needs to go back to Fe2+. Well, this is where we use our iodide ions. Bish bash bosh. Look at that. Having a great time. And 2, 1, 6+, 4+, 4+. Good. Balanced. So we can see now this stuff. You don't have to add Fe2+. You could add Fe3+. If you look, that would still react with the iodide to produce Fe2+, which would react with the peroxidized sulfate and be reformed with Fe3+. So bear in mind, you could add either of those. But generally speaking, I think it's Fe2+ would be what is added, but either would work. That is that reaction done. Make sure you know it. That's what I would say there. The other homogeneous reaction, which is possibly the more common one, because it comes under the term of autocatalysis as well. And this is the reaction of MnO4- with C2O4 2-. So the manganate ion with the ethane diione ion. This is what's called autocatalysis. Now the overall reaction is as follows. Just bear with me, it's not a particularly short one to write out. Nice redox equation there. It's obviously all very heavily sort of involved in redox, as I said at the start. With the variable oxidation states, we've got electrons being transferred all over the shop as this happens. So you've got that, and 10CO2. Slow reaction. These two again are negative, therefore there's repulsion present, therefore they are not going to react as quick as they could do in, well, if they were differently charged or oppositely charged. But what we find here is we don't have to add a catalyst. The manganese ion, the manganese 2+ ion, is actually a catalyst itself. So the slow reaction produces a catalyst, which ultimately speeds up the reaction. So it's auto catalysis. It auto catalysis. It's auto catalyzing. It catalyzes itself using this manganese 2 plus ion. And what happens is, initially this reaction has to happen. You have to produce the manganese 2 plus. So this is the initial reaction, regardless how you look at it. But then the manganese 2 plus gets involved, and it reacts directly with the manganate ion. And again, not a particularly short one here. That's occurring, and 4H2O. That's our first step. But again, look, it's got to be catalysis, therefore this has got to be reduced. This 3 plus, which has been formed in the process, has to be reduced. So we stick that in next, and that's got to go down to Mn2 plus, and we do that using the C2, the O4, C2, the C2O42 minus the ethane diolate. So this is an autocatalysis reaction. We find slow reaction there, but ultimately it forms the catalyst for the reaction, which then gets involved, reacts with the manganate, forming the manganate 3 plus. That then is then used to react with the ethane diolate, which reduces the manganese 3 plus to the manganese 2 plus. Overall reaction obviously is as can be seen there. So it's a very specific example of a homogeneous catalyst, but one they like. There have been questions in the past that have talked about. I've got another line down here. Stop drawing lines, that would help. And I'll draw a graph of this reaction because it's quite an interesting one. Oh, actually, no, it's not at all. It's completely uninteresting. Oh, lasso. So if you have an axis or axes, this one we could say would be the concentration of manganate ions. This one is just time. Initially, because we've got this slow initial reaction because of the repulsion, we would find it kind of starts, goes, and then we would hit a steep bit, and then we would level off. In terms of explaining this, slow because of the repulsion. Here we've got the Mn2 plus being produced, and then we've got catalyzing, but then it slows down at the end. Well, that's because basically we run out of reactants. Now it could be that this drops to 0, it could be that our ethane diolate drops off, it doesn't, whatever. The point is we're running out of reactants, so the reaction obviously naturally comes to sort of an end, if you like. So slow because of repulsion, speeds up in the middle, this fast, much steeper gradient here because of the fact that we're producing the catalyst in this autocatalysis reaction. Finally, finishing up with it being used up, and therefore it has a much shallower gradient, which ultimately will just hit a flat line, it will plateau out. And that's really catalysis done. There's not a lot there. There are the odd bits of application. I'm going to look at a couple of exam questions, one that shows the sort of basic introductory nature, and one which is very much based around application. So I'll whack them up now. Okay, so the first one we'll look at is, I don't know what this is now, I think it's from June 10, it's question 3 on the June 10 Chem 5 paper. And it's quite nice, sort of standard, and it's one of these, you can see here, we've got the iron 2 ions catalysing the peroxidized sulfate ions and the iodine ions. But it gives you some nice sort of standard stuff you need to know. So, something like this, state the meaning of the term homogeneous. So we're looking for the idea of same phase, like I said previously, or state. Suggest why ions from S block elements do not usually act as catalysts, because they do not have variable oxidation states. Whereas our transition metals do. Write an equation for the overall reaction. I'm not going to go through this one because it's one that I've already showed you there. It's the I minus ions reacting with those to produce the sulfate ions and the iodine molecules. Give one reason why the activation energy for the reaction is high. Well, they have a negative charge, therefore there's repulsion. That's because negative charge. Don't need to use exclamation marks in exam this, unless the examiner shouts it. Write two equations to show exactly as I showed you previously. The idea of Fe2 plus ions going there, becoming the Fe3 plus, and then being turned back into the other. 3 there, so the second part suggests one reason why the activation energy for each of these reactions is low, because we've got attraction. They're oppositely charged ions. We've got positive ions here in both of those equations, Fe2 plus and Fe3 plus. So in this one we've got Fe2 plus with the S2O8. This one we've got Fe3 plus getting involved with the I minus. Attraction there, nice low activation energy. We don't take a lot of energy for those to actually come together. Reason therefore is because they're oppositely charged. There is a nice little one here, 3F. Explain why Fe3 plus ions are as effective as Fe2 plus ions in catalyzing the reaction. Well, the reason for that is that these reactions, as I said before, and I will just fill these out quickly, can occur in any order. There's no reason that this has to happen last, this has to happen first. It can happen in any order because we're ultimately producing the same things no matter what happens. Fe3 plus goes to make the 2 plus, which goes back to 3 plus, and vice versa. So the Fe3 plus ions, Fe2 plus, either reaction can occur in any order. So we could add Fe3 plus or Fe2 plus, and we get the same catalysis occurring. That's a reasonably simple one. They've kind of, if you know about the reaction between the peroxidized sulfate and the iodide, you're going to find this question a lot easier. But they are also sort of walking you through it slightly. The next one is a little bit more difficult. It's a more application-heavy question from June 2013. So this is really quite application-heavy, but I like it. So this question explores blah, blah, blah. Ethanol is oxidized to ethanoic acid by oxygen. This reaction here, the equation is there. But this reaction is slow at room temperature but speeds up in the presence of cobalt compounds. So we're using cobalt as a catalyst. Good. So we'll explain why it is able to act as a catalyst in this process, number one. Then illustrate your explanation with two equations to suggest how, in the presence of water and hydrogen ions, CO3 plus and then CO2 plus ions, catalyzing this reaction. Okay, so that's what we're trying to do on here. We're trying to explain all these bits. It's one of these where it's broken it down to a few bits. Now, these are sort of your questions here. So first of all, explain why it's able to act as a catalyst. So cobalt, variable, same thing again, oxidation states. Great. And ultimately, we need to give this idea, and this is probably a sneaky little mark there, lowers activation energy or provides a route at a lower activation energy. Either of those is fine. This is, I think this is it's a tricky question, this, but it actually, when you look at it, I think it's based around the contact process. So we look at the contact process, the SO2 becoming SO3 using the O2. That has a similar thing with two equations. One where the oxygen isn't involved, and the next where the oxygen is involved to reform the catalyst. Now it says, illustrate your explanation with two equations to suggest how, in the presence of water and hydrogen ions, CO3 plus and then CO2 plus ions could be involved in catalyzing this reaction. So we know, first of all, well, we know that our cobalt ions must be reduced, which means whatever it's reacting with must be oxidized. Well, that's our oxidation, I should say there. So our first reaction involves CH3 CHO becoming the CH3 COOH with CO3 plus. Now obviously that's not the full reaction. We've got to balance it up. We've obviously got to include the fact that this is going to get reduced. That's capital with a little. That's getting reduced there. This is what's being oxidized. We've got to balance it up with, as you would normally do, so we end up with 2H plus here, 2 there, 2 there, and a water there. And it does say you need to use the presence of water and hydrogen ions. So that's our first bit. That's very similar. Excluding the water and the hydrogen ions, that's almost the exact same type of reaction that was involved in the contact process. We're just having to use the water and hydrogen ions to balance everything up. Then finally, we need to reform our catalyst. So our CO2 plus, why do I keep doing it like that? Needs to be turned back, dear me, in a CO3 plus, and this is where our oxygen gets involved. So there's our O2 molecule. But then again, we've got to balance it up. So H2O on this side, half of that, and we're going to have 2H plus on there. And that's actually it done. That is the entire question done. So it's very application heavy. You're not going to learn this, but it's using that sort of idea of the heterogeneous situation of the sulfur dioxide becomes sulfur trioxide in the contact process. It's applying that. That's my feeling here to a different situation, which actually it's at the end of the paper. It's one of the harder questions. I think this is the section B part, so it is one of the harder questions, which therefore means the application is, is going to be more intense. But I don't actually think it's too bad of a question, particularly once you see it and work out what's going on. And if you know your catalysis, then this shouldn't be too bad at all. But that's it. That is catalysis. So I think that's been a reasonably quick video. It's perhaps not at all. I don't know. But there you go. If any problems, obviously, stick a comment in. But yeah, I hope that's been of some help.